Tests for independence introduces statistical methods used to determine whether relationships exist between variables in financial and economic data. In investment analysis, analysts frequently need to evaluate whether movements in one variable are associated with changes in another. Examples include examining the relationship between stock returns and interest rates, inflation and bond yields, or portfolio returns and market benchmarks. Tests for independence help determine whether observed relationships are statistically significant or merely the result of random variation. The topic emphasizes that identifying dependence among variables is essential for forecasting, portfolio diversification, risk management, and empirical financial research within modern investment analysis. The topic begins with parametric tests for correlation, particularly tests involving the population correlation coefficient. Correlation measures the strength and direction of a linear relationship between two variables, with values ranging from -1 to +1. A positive correlation indicates that variables tend to move together, while a negative correlation suggests inverse movement. The topic explains how analysts test whether the population correlation coefficient differs significantly from zero. If the null hypothesis of zero correlation is rejected, analysts conclude that a statistically significant linear relationship exists. These tests are especially important in finance because diversification benefits depend heavily on correlations among asset returns. The topic explains that parametric correlation tests rely on assumptions regarding the underlying distribution of data. Typically, the variables being tested are assumed to follow a bivariate normal distribution, and the observations should be independent and randomly selected. Analysts calculate a test statistic using the sample correlation coefficient and compare it with critical values from the t-distribution. The topic highlights that larger sample sizes generally produce more reliable estimates and stronger statistical power. Understanding these assumptions is important because violations can reduce the accuracy of test results and lead to incorrect conclusions regarding relationships between financial variables. The topic also introduces non-parametric tests of independence, which are useful when data do not satisfy the assumptions required for parametric methods. Non-parametric tests are less sensitive to non-normality, outliers, and skewed distributions frequently observed in financial data. One commonly used approach is the rank correlation method, which evaluates whether variables exhibit consistent directional relationships rather than strict linear dependence. These methods are particularly valuable when dealing with ordinal data, small samples, or return distributions characterized by heavy tails and extreme observations. The topic emphasizes that non-parametric tests provide greater flexibility while sacrificing some statistical efficiency compared to parametric techniques. Another important topic covered in the topic is contingency table analysis, which examines independence between categorical variables. Contingency tables organize observed frequencies into rows and columns representing different categories or outcomes. Analysts then use chi-square tests to evaluate whether the observed frequencies differ significantly from those expected under independence. In finance, contingency table analysis can be applied to credit ratings, economic classifications, market regimes, or investor behavior studies. The topic demonstrates that categorical independence tests help analysts identify patterns and associations in non-numerical data, broadening the range of statistical tools available for financial research and empirical analysis. The topic highlights the practical importance of tests for independence in portfolio management and risk analysis. Correlation and dependence relationships influence diversification effectiveness, asset allocation decisions, and portfolio volatility. Assets with low or negative correlations can reduce portfolio risk, while highly correlated investments provide fewer diversification benefits. Similarly, identifying relationships between economic variables improves forecasting models and investment strategies. The topic emphasizes that analysts must interpret statistical significance carefully because correlation does not necessarily imply causation. Sound financial judgment and economic reasoning remain essential when applying independence tests to real-world investment and market analysis. The key concepts from topic establish an important foundation for understanding relationships among financial variables. Parametric and non-parametric tests of independence provide analysts with methods for evaluating correlations and associations systematically. Contingency table analysis extends these techniques to categorical data, allowing broader applications across finance and economics. These tools support advanced quantitative methods throughout the CFA program, including regression analysis, portfolio optimization, factor modeling, and risk management. Mastery of tests for independence enables investment professionals to identify meaningful relationships in data, evaluate diversification opportunities, and improve the reliability of empirical financial research and decision-making under uncertainty.